So the first talk is by Monika Aidelsburger, and she'll be talking about cold atoms and engineering gauge fields with them. So please go ahead, Monika.
Thank you very much. As mentioned, I will speak about quantum simulation with cold atoms, in particular engineering artificial gauge fields. And I'd like to present some work that we were mainly working on last year in realizing Fouquet topological phases. And so just to set the stage and remind everybody how our experiments look like, we work with cold atoms, which are cooled down to temperatures on the order of a few nanokelvin. And then we prepare them in periodic potentials that we realize by interfering laser beams. So this is just one simple configuration as an example where we have two counter-propagating laser beams that generate a periodic potential with a lattice constant λ/2. And so these systems are very convenient because if we describe the dynamics, it turns out that those are described in terms of Hubbard models. So depending on the species that we work with, we can either realize the Bose or the Fermi-Hubbard model. So we have a hopping matrix element J, the kinetic energy term between neighboring sites, and an interaction energy term if the atoms sit on the same site. So we have this very nice model system, which is very nicely isolated from the environment, and which we can manipulate in terms of controlling the parameters because we just assemble it directly in the lab using a bottom-up approach. And what we have been interested in using these systems in order to study topological phases of matter. And obviously, we have been very much inspired by the work or the phases that have been discovered in condensed matter physics. And in particular, so this is just a very small overview, but in particular, we have been interested in realizing integer and fractional quantum Hall systems. So what we have in mind is mimicking or simulating the Hamiltonian of a two-dimensional electron gas in the presence of an external magnetic field with our cold atom systems. Now, naturally, we only have real hopping matrix elements between neighboring sites, so we have to find other ways in order to mimic these types of Hamiltonians since our atoms are charge neutral. And so if we take this very simple example of electrons in a periodic potential with external magnetic field, we can think about the Hamiltonian that we need to mimic for our systems. And so if we now just look at the non-interacting Hamiltonian, we typically have this Jij hopping matrix element between nearest neighbors. But now if for electrons we turn on an external magnetic field, then we know that these tunnel coupling matrix elements become complex. And we have these Peierls phases that appear in the matrix element, which is connected to the vector potential that generates the external magnetic field. So now if we calculate the Aharonov-Bohm phase around a closed loop, which on the lattice just means summing the discrete phases on the four different bonds, then we can associate this phase with an external flux that is piercing the unit cell, here written in terms of the magnetic flux quantum phi naught. So essentially all we have to do is engineer this complex hopping matrix elements or these Peierls phases phi. And then since we use laser-assisted tunneling techniques or periodic driving, those phases are naturally on the order of 2 pi or pi. So we can realize very large field regimes entering, for instance, the interesting regime where the Hofstadter butterfly occurs in the Hofstadter model, which describes square lattice in the presence of a uniform magnetic field. So the technique that we have been developing in the lab, or that we have been using in the lab, of course, it's not new. Other groups have done that before us, also in different contexts. But the technique we are using is Fouquet engineering. So we take our system's parameters and drive them periodically in time with a driving period that is denoted here as capital T. So this means that we can use Fouquet's theorem in order to describe the time evolution after one driving period. So here the time evolution operator for one driving period is expressed in this form, where we have this new effective time independent Fouquet Hamiltonian appearing in the exponent. So if we actually probe our system only after integer multiples of the driving period at stroboscopic times, we effectively mimic a time evolution according to this effective time independent Fouquet Hamiltonian. And then the idea is to find a suitable driving protocol that allows us to engineer this Fouquet Hamiltonian with the properties that we are interested in. Now, if we actually do that and work with this explicitly time-dependent system, time periodic system, then our eigenenergies are only defined up to integer multiples of the driving energy quantum h bar omega. So we are actually working with quasi-energies which we can either plot in this extended Fouquet zone scheme, where now we have one engineered dispersion relation around zero energy, and then multiple copies of this dispersion relation separate by h bar omega, or as we typically do, we plot it in a reduced Fouquet zone scheme and only consider quasi-energies between minus h bar omega half and plus h bar omega half. But we should keep in mind that actually the eigenenergies are only defined up to integer multiples of h bar omega. Now, these techniques have been used by our group, but also by other groups in order to engineer very well-known topological lattice models. So one example is the Hofstadter model, where here you see that there's a complex hopping matrix element for hopping along the x direction. So here M is the lattice index along x and N is the lattice index along y. So this realizes a square lattice in the presence of external homogeneous magnetic field, which has the famous single particle energy spectrum known as the Hofstadter butterfly, and where we know that there are many different topological phases that depend on the external flux, but also on the filling fraction. And the second model that I want to mention is the Haldane model, where the unit cell is pierced by a zero net magnetic flux, but there's a staggered flux in the unit cell, and complex hopping is between next nearest neighbors. And there's also an energy offset, sublattice energy offset between A and B sides, where the A and B sides are here shown as black and white dots. So also in this case, we have topological phases that occur in the phase diagram, and both have been studied with cold atoms, but also with other synthetic quantum systems. And just to mention, this idea of periodic driving in order to engineer new interesting phases of matter has been applied to many other systems like superconducting circuits, but also coupled waveguide arrays, now also to real solid state materials such as graphene. And in a more abstract sense, you can find similar ideas again in using this concept of synthetic dimensions, where now one real lattice axis would be replaced by a different degree of freedom. So for instance, by a different internal state, like different hyperfine states, different Zeeman levels, which are then also coupled by additional laser beams. Again, this is then used in order to engineer the Pyers phases. Okay, so let me just briefly remind you how we describe the topological properties of the energy bands that we engineer by periodic driving. We work in quasi-momentum space, so the Chern number, the topological invariant of the band, is defined as the integral over the Berry curvature. And the Berry curvature then is a measure of the curvature or the winding of the eigenstates across the Brillouin zone. So U here are the cell periodic Bloch functions. And what is nice in our synthetic quantum systems is that we can actually cook up measurement protocols that directly allow us to measure the Berry curvature or the winding of the eigenstates as a function of quasi-momentum. And so here I just want to briefly give you a list of protocols that we have developed in the past, our group, but also other groups, just to give you an idea of what we can do. So the first one I want to mention is interferometric measurements. So here the idea is that we can prepare wave packets in quasi-momentum space with a very well-defined mean quasi-momentum. And then by applying forces to our wave packet, we can build interferometers. So we can split the wave packet, for instance, by using two different internal states, and then make the two parts of the wave packet travel along different paths in the dispersion relation. So we open the interferometer in quasi-momentum space, and we can also close it again and read out the Berry phase at the end of the interferometer sequence. And this phase that we read out is then directly related to the Berry flux that is piercing the area of the interferometer. So now by changing the area of this interferometer and changing the initial and final point of the interferometer, we can map out the Berry flux across the full dispersion relation. Now I will also focus a bit more on transport measurements in a second, but before I do that, let me mention another technique that have been implemented with fermionic atoms, where you can use state tomography in order to directly map out the Berry curvature in quasi-momentum space. So here you see the Berry curvature in the first Brillouin zone of a hexagonal lattice, which has trivial topology. So here the Berry curvature, positive Berry curvature is shown as red and negative Berry curvature is shown as blue. So if you would sum up all of these points, the Chern number would be 0. But again, what I want to focus here on is that you can extract, using the state tomography technique, the Berry curvature quasi-momentum resolved if the fermions populate the full band, for example. And then there have been a lot of other techniques from quench dynamics or machine learning that make this extraction of the Chern number and the topological invariance more efficient and allow us to map out the full phase diagram, for instance, of the Haldane model. Now, we have been using transport measurements. So the idea is that we prepare a cold cloud in the lowest energy band of our model. And then we apply a force to our atomic cloud. So now if we describe the equations of motion in a semi-classical framework, where again, we assign a well-defined mean quasi-momentum and mean position to our wave packet, then we find that first of all, there's a band velocity according to the derivative of the dispersion relation along the direction of the force, which if all the quasi-momentum states are populated, averages to 0. So in fact, if we apply a force to our atomic cloud, there will be no net motion in the direction of the force that we apply. Then on top of that, there's a contribution to the velocity transverse to the applied force, which is proportional to the Berry curvature. So here F denotes the strength of the force and omega the Berry curvature as a function of quasi-momentum Q. So again, now if we populate all quasi-momenta, the center of mass motion that we will get is the integral over all of these anomalous velocity components. So what you find is an integral over the Berry curvature of all populated quasi-momentum states, which is all states within the first Brillouin zone, which means that actually for the equation of motion, we find something that is proportional to the Chern number of the band where we have prepared our atoms in. So that means if we prepare our cold cloud initially in the lattice and apply our force, we can take snapshots of the center of mass motion of the cloud. And from this transverse motion, we can then extract the Chern number of the band. And this is one example of a measurement that we have taken in 2015, where you see indeed, oh, sorry, I have cut the axis labels here. So that's actually the center of mass motion in the vertical, along the vertical axis, and the evolution time along the horizontal axis. So you see that the cloud starts to move transverse to the applied force, and then it saturates at some point, which in our case is due to heating. So we find repopulation between the bands, which leads to a saturation of the whole motion in our case. And here phi equals 0 means that we switch off the artificial magnetic field. So here indeed we see that without external magnetic fields, the cloud does not move at all. So from this measurement, we were actually able to extract the Chern number of the band. But as you can see here from the equation for the anomalous velocity component, we can also use it to extract local information about the Berry curvature by not populating all the quasi-momentum states at the same time, but by only preparing a wave packet at a well-defined mean quasi-momentum, and by moving it only across short distances within the dispersion relation. So for instance, as you can see here, for these two different Berry curvature distributions, now it doesn't really matter for what phases I have picked these examples, but you can see that here in the center at Q equal to 0, for instance, there's like no Berry curvature, while in this other example, there's negative Berry curvature concentrated at Q equal to 0. So now imagine that we do an experiment where we prepare a wave packet shortly on the left of the Q equal to 0 point, we move it through, which means in this case, we would not expect an anomalous transverse velocity component, while in the second example, we would expect a deflection of the cloud. So by doing that, we can get information or local information about the Berry curvature distribution also from these transport measurements. Okay, so all of these techniques that work very nicely also for periodically driven systems have been used in order to mostly study the topological phases of the Hofstadter model, but also of the Haldane model. But now it turns out that in these periodically driven systems, we can engineer phases that otherwise do not occur in static realizations. So despite or like apart from this technique that is useful for emulating the physics of static models that we can otherwise not simulate in our cold atom systems, such as the quantum Hall effect, we can now study new phases. And something that I want to emphasize is that in the quantum Hall case, or what I mean the static case, we have this well-known bulk edge correspondence. So we know that if all the Chern numbers of the bands are known, we also know the number of edge modes at a topological interface, for instance, between a topological phase and vacuum, or between two distinct topological phases. So this is directly connected to the Chern number of the bands. But now in driven systems, we speak about generalized bulk edge correspondence. And the reason why the situation is different is that we are dealing with this quasi-energy spectrum, which again here is plotted in the reduced Fouquet zone scheme between minus h bar omega half and plus h bar omega half. And these 2 points at the edges of the Fouquet-Brillouin zone, they are actually equivalent. This means that now we can have edge modes that wrap around the Brillouin zone. So there's no notion of a true lowest energy band. Even for the lowest band, there can be an edge mode entering from below. So this can lead to a very peculiar situation where now we have 2 bands with Chern number equal to 0, but nonetheless, we have edge modes in the gap. And this is what we know, or what we call modified bulk boundary correspondence, which is predicted to also give rise to new phenomena. So for instance, we believe that in the presence of disorder, this anomalous phase turns out to be more robust, even as compared to conventional quantum Hall systems, which is also something that we are interested in studying. So there's a very simple picture, actually, how one can understand how these new phases arise. And one example that has been developed in the very beginning was the stepwise modulated square lattice. And in this example, I want to explain or walk you through a very fine-tuned situation, but of course, the idea is much more general than that. That is, we turn on hopping only along the colored bonds in this circular manner. And we have here a square lattice with AB sublattices. And now you can turn the modulations such that each step corresponds to one tunneling event. So if you prepare a wave packet on the black side, for example, during the first quarter of the modulation cycle, the wave packet has enough time to exactly tunnel over to the white side. And the same happens for the blue, green, and yellow bonds. That is, if we follow one modulation cycle, actually nothing changes. The wave packet returns to its original position. So the Fouquet, or the stroboscopic evolution operator, is simply the identity. And our effective time independent Fouquet Hamiltonian is completely trivial. Okay, it vanishes, it's equal to 0. So we would not expect any non-trivial physics to happen whatsoever. But now it turns out that if we look at the edges, something interesting happens. So if we now prepare a wave packet at the edge of a finite sample, we find that it can only travel along one direction if we follow the modulation protocol that I've just explained. So we have, in this fine-tuned situation, actually 2 degenerate bands with trivial topology around 0 energy. But nonetheless, we find 2 edge modes that wind across the Fouquet-Brillouin zone. And as you can already see from this simple example, the properties, or what happens at the edges, is encoded in what we call the micromotion. So we need to take into account what happens at the individual steps during the modulation protocol. So this is also the reason why this interesting phase only occurs away from the high frequency limit. So it actually only occurs when the modulation frequency is on the order of the other energy scales in the system. And in order to compute the new topological properties, we have to take into account the full time dependence of the evolution operator. It's not enough to simply take the time independent Fouquet Hamiltonian and diagonalize it and study the topological properties of the quasi-energy spectrum in the reduced zone scheme. Now, this has been studied first in photonic systems, coupled waveguide arrays. And we have implemented it in periodically modulated honeycomb lattice. And just to conclude how to characterize the topological properties of these new driven systems, I already mentioned that it's not enough to compute the Chern numbers. Instead, we need to look what happens in the gaps. So there are now 2 winding numbers that count the number of edge modes within a certain gap. So if we want to characterize the topological properties of our driven system, we need to find a way to measure these winding numbers. Here's the model that we have implemented. So we work with bosonic potassium atoms in a honeycomb optical lattice. And we have implemented a modulation scheme where we increased tunnel coupling along the red bonds, and we modulate it in this chiral manner. So we first increase hop along this red bond, then this one, and then this one. And in our case, we don't choose a stepwise modulation protocol, but a continuous modulation scheme. And it turns out that experimentally, that's relatively straightforward to implement, because the honeycomb lattice is generated by interfering 3 laser beams under an angle of 120 degrees. And if you have equal intensities, you get a nice symmetric honeycomb lattice. But if you decrease the intensity of one of these 3 beams, you imbalance the lattice such that hopping is increased along one specific bond. So now we can implement this continuous modulation scheme by periodically changing the intensity of the individual laser beams. So here you see the cosine modulation for the intensity of beam 1, 2, and 3. So we do that out of phase. This gives us this chiral modulation scheme. Now here are the phases that we find as a function of the modulation frequency and the modulation amplitude. So in the high frequency limit, actually what happens that is that in our graphene dispersion, we open the gap at the direct points and we realize the well-known Haldane model. So in this case, we find an edge mode around 0 energy, and the topology of the 2 bands are characterized by Chern numbers that are plus or minus 1. And in the high frequency limit, actually there's repetitions in the extended Fouquet zone scheme. They are very far apart. So h bar omega is a large energy scale, so these copies are very far apart. Now, if we decrease the modulation frequency, we actually move these copies closer and closer together until there can be a band touching point between Fouquet zones. So at this point, we cross, or we have a topological phase transition, and we cross into a new phase, which is particularly this anomalous Fouquet phase that I've mentioned before. Because we now had this band touching point between Fouquet zones, we have generated an edge mode at the edge of the Fouquet-Brillouin zone. But we have not limited the one around 0 energy, so now we have this anomalous phase where the Chern number of the 2 bands is equal to 0, but nonetheless we have this edge modes in the 2 gaps. And then there's a series of other phase transitions if we decrease the frequency further and further. So the next one that we have studied is this Haldane-like phase, where again we have Chern number plus and minus 1, but now we have an edge mode between the Fouquet-Brillouin zones and no edge mode around 0 energy. Okay, so now the question is, how can we characterize these winding numbers in our experiment? And the protocol that we have chosen to implement is starting from the high frequency limit, the Haldane phase, which has been known for a very long time and which has been carefully studied in many different experiments. So this limit we understand very well. We have 2 bands, Chern number plus and minus 1, and an edge mode around 0 energy. So the winding number between or at the Brillouin zone edge has to be trivial. There's no edge mode, so this one is equal to 0. And we have winding number 1 around 0 energy. And then the idea is to use this as a starting point and then track the topology of the gap closing points to study what happens at the phase transition in order to track the topological properties of the phases that are connected to this original Hamiltonian in the high frequency limit. So we study this white line across the phase diagram. So this is the same one that I've just showed you before. But now the colored lines show you the energy gap at the gamma point at Q equal to 0, which is where the gap closing point happens. So this black line is where the gap vanishes and the topological phase transition to the anomalous regime occurs. Again, here, very high frequencies, we have the high frequency limit that is the Haldane phase. Okay, so how do we track the topological properties across the phase transition points? So along this white line, we can assign this new parameter lambda.
Monika, just to interrupt, you've been now it's 25 minutes.
Yeah, okay. I will speed up a bit. So this lambda parameter actually characterizes this white line across the phase diagram. So at the gap closing point, we can actually assign a topological charge to this gap closing point itself, which determines how the winding number in a specific gap changes. So in order to understand how the winding numbers changes, we need to measure the topological charge. And what is also important is to identify which one of the gaps closes in the spectrum. And then we can actually extract this value of the topological charge from our local transport measurements, where we extract the sign of the Berry curvature. So here I'll be a bit more quick and just give you the final result. So this is what I explained before. We can use our transport measurements to extract the sign of the Berry curvature or Berry flux at a certain point in a dispersion relation. And specifically, we look at the gap closing point. And then the sign of the topological charge is actually encoded in how this sign of the Berry curvature changes across the phase transition point. So we can use our local transport measurements in order to extract the value of the topological charge and track how the winding number changes across the phase transition point. So let me briefly show you one of these measurements results, where we have measured the energy gap as a function of our modulation parameters to pinpoint where the phase transition happens. And in this case, you see the energy gap at the gamma point. And we have two topological phase transitions here and here. And also, just from the way we implement this measurement protocol, we can actually also identify which one of the gaps closes, if it's around zero energy or between Floquet zones. So we can already use this to pinpoint where the phases are, which gaps close. And now here I show you these local Hall deflection measurements, which we use in order to measure the topological charge at the phase transition. So we start over here, the Haldane phase, winding number 0 between Floquet zones and 1 around zero energy. Here's an example of the Berry zone and the Berry curvature distribution. And the phase transition point happens at this vertical line here. So just before the phase transition, we have a pi Berry flux developing at the gap closing point, the gamma point, which changes sign. And the sign change we can extract from our local Hall measurements, which allows us to extract that the winding number between Floquet zones changes by 1. And the same we can do for the second phase transition, where again, we have a sign change from positive Berry flux to negative. And at this point, we can extract that the winding number around zero energy has to change by -1. So from this combination of energy gap measurements and local Hall deflection measurements, we can extract the full set of topological invariants characterizing the phases, which are here the winding numbers shown below. And from this, we can then identify that this is the anomalous phase that indeed we wanted to realize, and that there's another Haldane-like phase on the left side. And so with this, I would like to conclude and thank all the people that have worked on this, especially Karen and Christoph, who have taken all the data in the lab, and our theory collaborators, Nur Ünal, Andre Eckert, Nathan Goldman, and Marco Di Liberto, with whom we have developed the modulation scheme and actually the measurement protocol. So thank you very much for your attention, and I'm happy to take any questions.
Thank you very much. There was a question already posted during the talk by Maria that I'd like to start off with. So Maria, please, can you just unmute yourself and ask the question to Monika?
Yeah, thanks a lot, Monika. A wonderful talk, but I'm always wondering with these artificial things, how do you know where the Fermi surface is?
Right. So actually, in our case, we have so far only probed the topology of the bands with bosonic atoms. So there, how you should think about these experiments is that we first prepare the condensate in a static periodic potential. So there we know very well, like what's the width of the wave packet, what's the lowest energy band. This is very well defined. And then we slowly start the modulation. And if we do the full time-dependent analysis of the energy bands, we can figure out which one of the bands is adiabatically connected to the one where we have prepared the static Bose-Einstein condensate in. So there's like an adiabatic continuation of this band, which then develops into the Floquet bands. This only works in this two-band example that I've told you. For the Hofstadter model, this is much more complicated because you start out with a square lattice that has the usual unit cell, one side per unit cell. You have your Bloch bands that you can calculate. But now if you introduce the artificial flux, the lowest one splits into several subbands. So there, this association of like which band develops into which one is a bit less clear. And then for fermions, we would do exactly the same. So for fermions, we know how to characterize the Fermi sea, the Fermi surface, and the Fermi energy in the static lattice. And then we would adiabatically connect it to the modulated bands. And we can play around with that actually. So you can prepare, depending on how you choose the modulation parameters, the Fermi sea either in like what we call the lowest band, or you can prepare it in the first excited band by just looking how the bands are adiabatically connected.
Okay, thanks.
Sorry, there's another question by Ted. Please go ahead.
Hi. Yeah, thanks. I have a very basic confusion about the whole framework of the Berry connection, which is not just peculiar to your talk, but actually it's a general question. I understand for single particle states how that is defined, and therefore how the Berry curvature is defined. But when you have a bunch of particles in a band and they're interacting with each other, I actually don't know what it means. Could you address that?
I think there are two parts that I would like to mention in my answer. So the first one is that for our bosonic systems, we make our life, so to speak, very simple, because we are really interested in probing the single particle properties of the band. We prepare a wave packet of many particles, but they are all as close to non-interacting as it gets. So we tune the scattering length to almost zero using a Feshbach resonance. So you can really describe it as a single particle Berry phase or Berry connection that you find. But then, of course, if you want to study something more interesting, like what we want to do, fractional Chern insulating states, for example, there we would prepare a true many-body state, like a Laughlin state, and you can define a many-body Chern number for this state. And usually, theoretically, how it's done is to introduce these twisted boundary conditions. In our case, people have shown that we can similarly measure this many-body Chern number by doing Hall deflection measurement, as I introduced in the beginning, but now for many-body state. I'm not sure that answers the question. But...
well, the first part is very clear. The second part, I'm still not sure. Maybe somebody could post or send me a reference where that many-body Chern number definition is explained. That would be helpful.
Yeah, sure.
Thanks, Ted. Next up the list is Adolfo. Please go ahead.
Hi, Monica. Very nice talk. Thank you. Actually, I was curious about something you mentioned kind of bypassing, but maybe it's addressable in experiment as well, which is the role of disorder. So you said that, these phases, you kind of mentioned that they're more robust to disorder. So I was wondering what you meant by that exactly. And the follow-up question would be, by tuning these lasers that you're showing actually in this slide already, can you make them not perfect to actually test how robust these phases to disorder?
Yeah, so thank you very much for that question. So that's actually something we have been working on during the last few months, and I hope to have some first results soon. So the idea is as follows. So we use the same modulation scheme, but now we add some optical speckle potential in order to study the robustness versus disorder. And what we are interested in is comparing the robustness in the anomalous phase and the Haldane phase, which you can both realize with the same model. And I think it's not so clear yet. What people have suggested is that the anomalous phase is more robust because, so more robust, I have in mind defining it with respect to the energy gap between the two bands. Like sort of as a measure of robustness, you can compare the strength of the disorder to the gap between the two bands. So that's like the first natural thing that comes to my mind in doing. And it has been suggested that this transition happens at larger disorder strengths for the anomalous phase, because you have this winding of the of the edge mode across the full quasi-energy spectrum, which is more robust and less easy to destroy, so to speak, as when you have like two bands with sternomer plus and -1, where you close the gap and you kill the edge mode in between. And moreover, including interactions, people have suggested that maybe there's even like a many-body localized phase present in these systems where you would still have topological edge modes, but a many-body localized bulk. And of course, something like this would be very nice to see. We are now first looking at single particle physics again by looking at the expansion of a wave packet in the presence of disorder, first seeing the disorder transition, and then also looking at the topological properties.
Thanks, very interesting. Thank you.
Thanks. Roni, like to ask you a question?
Yeah, hi, Monika.
Hi.
I have a question. Maybe you mentioned I got disconnected in the middle of the talk, but about non-Hermitian generalizations for all of this, and if you can use similar techniques and tweak the parameters to make the models non-Hermitian. And I'm mostly interested from the perspective of wave packet dynamics for non-Hermitian systems that has completely different properties. And since you can probe anomalous velocities and things like that, have you thought about this? I mean, there's no adiabaticity and everything, but still it might be possible.
Right, so I haven't really thought about it yet. The thing that we can do relatively easily is like adding dissipation via three-body losses or maybe scattering of photons. That is something that we can do relatively easily. But I have not yet thought about how this would actually change the properties of the system. But if you have some good ideas, I'm very happy to discuss.
Okay, that's awesome. Thanks.
Thanks. René?
Yeah, thanks for a really nice talk. I got two questions.
Yeah.
First question is, can you do, I guess you can do violent Dirac semi-metal-like structures, right?
Not super easy. I think there's some ideas on how to do that. It's not, no one has done it yet in our system, at least.
Okay, good, but maybe it's within reach, yeah. And so then my question would be, is it possible to induce artificial electric fields so one could also study the structure of the chiral anomaly and things like this?
Yeah, it depends very much on the model and how the artificial electric fields look like. In principle, we can do artificial electric fields. That's not something super difficult to do, but it depends very much on the model. The complexity lies in realizing the Y semi-metal band structure.
Okay. So I gather from your answer that this is kind of a new direction where not much is known so far.
Yeah, I think people have not yet done a lot along these lines. In other synthetic quantum systems, yes, or in other synthetic systems, yes, but not yet with cold atoms, also because many detection techniques have been demonstrated for 2D systems.
Mm-hmm.
And yeah, so one has to see. It's not super clear, I would say.
Okay. So what are the other synthetic systems where Y semi-metal-like behavior has been observed already?
Well, I don't know, but I think in acoustic structures, band structures like that have been realized. I think Ronnie probably knows more about this. I'm not an expert, but I know that this has been realized.
Yeah, okay. And so my second question would be, this is something that we are kind of interested in. I'm from the ADS-CFT community. So can one also generate lattices that effectively act like a non-trivial geometry? Let me put my question like this. So the hopping is somehow such that the effective field theory would be moving on a non-trivial background metric, ideally negatively curved, something like the hyperbolic plane or something like this.
I think I'm not the right person to answer this question. I'm sure there are ways one can think about engineering this, but I don't have a specific example how.
Okay.
I think this should be possible in what people call topoelectric circuits, which is
that I'm familiar with. Yeah.
So I think in those systems, I think there are people trying.
But what are the minimal ingredients that one needs? Like, what would you need to be able to do?
So for example, if you want to cover the hyperbolic, the Poincare disk, which is the negatively everywhere negatively curved space, which is homogeneous and isotropic. If you want to cover that with a lattice, there are classifications of that, and basically the curvature is basically in the connectivity of the lattice points. And then if you, let's say, put a kind of a hopping Hamiltonian, boson Fermi like Hubbard-like hopping Hamiltonian, then it will feel this curvature. Okay, so what's really hard is to generate this. I mean, maybe what's hard from your point of view is to generate this lattice with this tessellation of the hyperbolic plane.
So, but then the hopping elements need to be spatially dependent also somehow. Or...
Yeah, no, it's more like there are some papers by this Princeton group from Koller et al. I forgot the other names, where they basically look at these hopping Hamiltonians. So the matrix elements are not the problem. The point is that the geometry is really in the connectivity of the lattice, and this is what. So basically, there are other lattices that cover the hyperbolic plane than what you are familiar with from the ordinary flat plane. Yeah. Mm-hmm. Yeah, I can send you these papers if you're interested.
Sure.
Yeah.
Okay. Thank you.
Thank you.